So let me first, Lizzie's outside, so thank the staff, Timothy Ruff, and one of our graduate students, Lizzie Silver, who's just done a great job doing all the organizing. And then Joe Ramsey, would you raise your hand? That's Joe Ramsey. Joe is the chief developer, architect, research, etc., for the Tetrad program, which you'll be using, right, in a hands-on this morning. Okay. So the goals of the workshop are to convey the rudiments of graphical causal models, in particular the way they occur in search, which is really the topic of the workshop. In fact, the topic of the workshop is not to really get you acquainted with the theory of causal model search, but to have a series of examples, case studies, where people have used causal model search in real scientific problem applications, right? So we have a number of talks ranging from economics to fMRI image analysis to genomics to educational research to climate change, etc. So the idea of this workshop is for any of you who are not already steeped in the theory to get you acclimated to the basics of the objects that we're searching for and the basic methods of search that we use to actually come up with these models. And the program that you'll be using Tetrad for has been under development in one way or the other for almost 20 years. So it's free, which means we can't guarantee that it's completely bug-free. But given it's free, it's incredibly robust and bug-free in my view. So I apologize if there's any bugs. I'm sure there will be some, but generally it works pretty well. And it's a program that's a complete causal modeling tool, which is why we're going to be using it hands-on. It allows you to build models, simulate data from those models, apply algorithms to those models, right? Look at the output and see how it compares to the truth that generated the data that you analyzed, and also analyze real data sets. And we're going to do both. And I've found that in giving these sort of workshops over the years, every time I give a workshop, I drop out a little more theory and just add on a little more hands-on stuff, because people get it much, much better if they actually get their hands on the program and actually build models and see how they work from the ground up. So I'm going to spend a lot of time demonstrating for you things that I do with the program and then saying, go ahead and do the same thing on your computer so you see how things work. And that will also hopefully equip you with the ability to play with the program later on your own. Because I think what you'll find is to understand what's really going on, you have to be able to build these models, specify what's true, apply the algorithm to it, and then see what the algorithm puts out, and then say, oh, this is the truth, and this is what the algorithm said, right, I get from the truth, and so I understand what the limitations are of the algorithm and what the strengths are as well. Okay, so hopefully all of you have already downloaded Tetrad from the website and it's running on your machine. And if not, here are the websites for getting it. And as I said before, there's a couple of files in the workshop directory that contain 2 data files we'll be analyzing in several sessions that you don't need, but you could benefit from having to save what's going on. So the 2 files that you'll need for sure are this tw.txt and charity.txt, in particular the charity.txt, which we'll be working on later on. Okay? So if you have computer problems, raise your hand. Joe will try to come around and help you. And then he's finite, I know, and if you still can't get everything to work, please find someone to sit next to who has a working wireless connection. Okay, so I'm going to try to motivate the topic for a few minutes, and then we're going to spend a bunch of time on what it is to represent causal systems, to build them, to actually generate data from them, to take a model, to estimate its parameters, to see if the model fits the data, and then to later, and really the second half of the morning, really spend the time on causal model search. So I put statistical in green font and causal in red to indicate that there's a difference between what we usually consider statistical or probabilistic information and what we consider causal, right, claims, causal hypotheses. And so one of the things that I think this project makes vivid is the separation between probabilistic or statistical facts, ideas, information, and causal hypotheses, and how the two get bridged either way, from causal hypotheses in terms of what they make predictions about statistically, and in terms of if you have statistical data and then you want to make inferences about causation, what you can do on the other end. So I try to separate the ideas by putting the statistical ideas in green and the causal in red to indicate danger. So there are three kinds of ideas that occur in policy, law, and science which require causal hypotheses quite crucially. Right? What are subjunctive questions? If you want to contemplate things you'll do in the future, right, actions you'll take, you need to have causal knowledge, right? Otherwise, it would be easy to cure lung cancer by having everybody wash the tar stains off their fingers because the association is quite strong, or it used to be anyway. And we know that wouldn't work. So in order to actually implement effective policies, causal knowledge is required. There's another whole set of questions that are usually considered in the law when something has happened and we want to hold someone responsible. We need to answer a counterfactual question. What would have happened had things happened or been done differently? Right? So those are the kind of questions that occur typically in law, and they require causal knowledge. And then there's a whole bevy of questions that happen in science, which are, what are the mechanisms are that run the world? How does the world work? And those are also usually requiring causal answers. The theory of scientific explanation for many years avoided causality, and it was really impossible to get a good theory going without it. And so in the last 20 years or so, the most popular theories of scientific explanation are all causal theories. The second thing I really want to emphasize is that part of what we do in this project is answer what we call the Rumsfeld question, which I don't like to use his name usually, but he did get a few things right. And in this case, right, we want to have good access to what we don't know and what we do know. And so in the Rumsfeld problem, we say, can we tell when there is or is not enough information in the data to answer a causal question? In surprising detail, we can answer that question quite precisely in lots of different circumstances. So I can tell you exactly, under a certain set of assumptions, what can and cannot be known about the causal structure generating the data. So the first thing to really make vivid is that when you're predicting and you have a passive observation before you, right, that's not the same as predicting from having an intervention that has assigned something before you. So we say the prediction from observation is not equal to the prediction from intervention. That's really one of the key insights that you have to really get to understand why causal knowledge is so crucial. So the example I like to use comes from the 1950s and 1960s, back when unfiltered cigarettes were common and people rolled their own cigarettes, right? And so if you smoked a lot, you had to get your fingers dirty in the tobacco by putting it into your cigarettes and rolling it up. So the amount you smoked could really usually be detected by how stained your fingers were. So if I said to you, what's the probability of having lung cancer in 1960, given you had tar-stained fingers in 1950, right, or did not have tar stains in 1950, right, I could be very confident I could predict, right, what your situation was in terms of lung cancer, much better if I had the information about your tar stains. But that's not the same thing as taking your fingers in 1950 and whatever the state of your fingers, washing them with tar soap so that your fingers were clean. So in the first case, I'm saying, what's the probability of having cancer given you have clean fingers in 1950? In the second case, I'm asking, what's the probability of having lung cancer in 1960 given someone washed your hands clean in 1950, right? So when I say wash your hands clean, I've hidden the information about what your hands started out to be. If they were starting out to be clean and I washed them, that's one thing. If they're starting out to be dirty and I washed them, that's another. In both cases, the intervention has assigned the value of your finger stains and has erased, in some sense, right, the information about what you actually had, which we could have had observationally. Okay, so these probabilities are not going to be the same, and that's important to know. So in general, the probability of a variable given we observe other variables is not the same as the probability given at least one of those variables has been set or assigned. And so we differentiate causal prediction from statistical prediction. And in non-observational data, if we have measurements that we did not intervene to set, and in background knowledge, we can do a lot in statistics to estimate the joint distribution of the variables that were observed. We'll call these X, Y, and Z. And from that joint distribution, we can derive easily conditional distributions which allow us to predict Y from X and Z. Right? So the task of the usual statistical prediction is kind of represented in this chain. If we want to make a prediction about what's going to happen if we set something, right, we need more. We need causal knowledge, and along with the distribution we might have estimated from the data and a causal structure, we can then use the distribution and the causal structure to predict the variable y, given we intervene to set y, set x, and then observe z. Okay, so that's in more general terms what we need in order to actually make these kind of interventional predictions. Okay, so in causal search, what we're trying to do is find or compute, excuse me, all the causal models that are indistinguishable given the background knowledge we have and the data we've observed. Right? So, I mean, there's several ways we can articulate that, but that's, I think, the basic idea. And once we have that, once we have all the models, right, that look observationally equivalent to us, we want to know if they share any features, because if they do share features causally, then that's what we can learn or know from the observational data. And if they don't share features, we can't know about those features, right? And I'll get into much more detail about that when we get into the program later. But the most common tool that's used for causal inference, and has been for 50 years, is multiple regression. And I want to stress and make it vivid to you in the course of the morning why that's the wrong tool for causal search. So I'm going to start with an example. Yeah?
Could I ask, do you include instrumental variables in that statement?
No, instrumental variables can be the right tool, especially if they're known to be actual instruments. Right. So let me give you an example to start you out and fix your thinking. So way back in the 1980s, there was this debate about whether foreign investment in third world countries helped those countries become economically developed and therefore less repressive politically, or the alternative theory went, foreign investment made them more dependent, right? The regimes became more corrupt and they became more politically exclusive. So a pair of sociologists weighed in on this question, Timberlake and Williams. They collected data on 72 countries, and for each country they measured the degree of political exclusivity. So the higher PO, the more exclusive politically. How much civil liberties you had, what freedom of expression, freedom of press, freedom of assembly, things like that. A measure of economic development was energy consumption per capita, and then FI was the level of foreign investment. And the idea was, what's the connection between foreign investment and political exclusion? Okay? So the correlations they measured were as such, and as you can see, the correlation between political exclusion and foreign investment is negative, which means higher levels of political exclusion, right, go with lower levels of foreign investment. So this is an embarrassment to their theory, because they were arguing, in fact, that foreign investment makes countries, right, less repressive, more repressive. And what they did was, of course, run a multiple regression in which political exclusion was the output, foreign investment was one of the predictors, and the control variables, or the covariates, were energy consumption per capita and civil liberties. So where the relationship in the marginal or the unconditional case was negative, more political exclusion with less foreign investment, it flipped in sign after controlling for these regressors, and now they argue that, in fact, more foreign investment leads to more political exclusion. So they were dependence theorists. And their interpretation was that it was causal, right? So we should actually, as a policy matter, not invest so much money in third world countries. So if we had to represent, right, in some sense, the generic version of their causal claim, there's the model that I think we would draw, right? And the coefficients I've listed next to them are the regression coefficients that go along with their estimates. So Fi is an arrow into PO, and the coefficient is 0.217, which means it's a positive causal influence. Now, if I search for alternative models, right, if I acknowledge the fact that this is their hypothesis, but there might be lots of other causal models that can actually explain the same data, and I do it with Tetrad, and we'll go back and do this later, right, I come out with the following sort of structure, which is a representation of an equivalence class of many, many possible models that share a certain set of features. So what this model or this equivalence class does say from these arrows here is that foreign investment is not a cause in any way of political exclusion. Right? These arrows mean that FI is not an ancestor of civil liberties, and it's not an ancestor of economic development, and so it's causally, right, an effect at best. And the fact that there's a double-headed arrow here indicates that there is some unmeasured common cause we might have left out. This circle here means we don't know about the nature of that part of the connection. Economic development might cause foreign investment, which would of course make sense, right? Or there might be some common cause between foreign investment and economic development. Now, if we're generous and we take one of the models that this represents and we parameterize it and we estimate its parameters, right, here are the numbers we get, and I'll go into this a little more later, but the basic idea here is that we can test whether this model as a causal structure fits the data. And the fit is extremely good because when you're looking for model fit, you want high levels of p-value, not low, and I'll get to that again in a little bit more detail later. And a regression model, in terms of its causal structure and its causal claims, is not testable because it entails no constraints on the data that we can check. Right? The only way that you can usually say, is my regression model any good, is if the amount of variance in the outcome variable that you've explained by the inputs is high. But the causal structure that you're actually specifying the regression model implies no constraints that I can test in the data, so as a structure, it's untestable. So not only have we found an alternative that contradicts the claims in the article completely, but it passes the goodness of fit test with flying colors. And it turns out there is no model with testable constraints that passes a goodness of fit test that agrees with their hypothesis. Okay, so I'm now going to actually do, right, the demo of the Tetrad program so I can show you how this works, and feel free to either work along with me or watch what I'm doing and then go back, right, and do what I'm going to do. So I'm going to do this. I'm going to load the data, estimate a regression, search for alternatives and estimate the alternatives, and then after that I want to have you load the data and estimate the regression, but not go ahead and do the rest, which I'll come back to later on. Yeah. Okay, so let me actually now demonstrate the Tetrad program. So when you load the program up, you get an empty workbench. You get an empty workbench, and there's lots of different boxes on the left side that allow you to build graphs, load data sets, do search, etc., etc. So in this case, I already have a data set sitting there on the side called tw.text. So to load it, I click on the data box, click to put an empty data box in the workbench, and then you'll notice it's gray, which means it doesn't have anything in it yet. So if I double click on that, it says, what do you want? And I say, yeah, fine, data wrapper is good. And now I have a data looking thing, but it's empty. I go to File and I say Load Data. And now I have to locate what directory my data file is sitting in, right? And so I've just stuck that into a data directory. And the file tw.text is this flat text file that contains, in this case, covariance data, exactly what I showed you on the previous slide about the correlations that Timberlake and Williams measured. If I say Open, it shows me in the window what the data file looks like, and then what I have to do to load this in is go to the left and say, well, what is the type of data I'm loading? Is it tabular in a squared column row matrix? No, it's covariance data. And then I have to say what kind of delimiter there is. White space means any. And don't worry about this for now. Don't worry about this. And then if I am satisfied, I say load. And if I don't get any error messages, I'm probably in good shape. And then I say save. And now I can see that I've successfully loaded this covariance matrix into Tetrad's data frame. Okay? So that's what it'll look like if you're successful. Now, what I want to do is first, right, estimate the regression model that they did. So I click on the regression, which is a special node, and then click on this arrow button in the workbench to connect the data into the regression module so that the regression will operate on that data. So when I do a regression, right, I click on the regression mode and it says multiple regression, fine. And then it prompts me for what is my response variable and what are my predictors. My response is going to be political exclusion. So I click on it and put it into response. And now I put in my predictors, right, and then I say go ahead and execute. And that's what I get. And so you can see that the coefficient estimate of foreign investment is 0.2277. P-value is 0.0002. It's highly significant, which means we can reject the hypothesis that it's 0, right? And so we can conclude, as they did, that foreign investment, even controlling for economic development and civil liberties, is a significant predictor of political exclusion. Okay. However, is it a cause? Well, to investigate that, let's do a search by putting a search module on there. So, okay, what I did so far is all I want you to do now. So I'm going to demonstrate the search, but you don't have to do that in this particular thing. All we want to do is get you at least loading the program and running it. So, but for me, I can put the data into the search node, click on the search, and then say, well, right, I want to run an algorithm, so I'll do FCI. I have to actually choose a significance level. This is a small data set, so I'll choose something a little bit more generous, and I'll execute that. And then if I put this in the approximate positions I've put, you can see, right, what output I'm getting from the FCI algorithm, right? And it's the one I showed you on the screen before. Yeah.
So you change all this alpha, so what's really the meaning of that? So how about you just put like a 1, and what happens?
Well, 1 would mean everything fails or rejects the test. I can never remember which way it goes. So the alpha value is what that figures in is in the algorithm on the way, it's doing tests of conditional and unconditional independence. And it's using the p-value, right, that alpha value I'm using, to either accept the independence hypothesis or reject it. So it's going to reject it at the 0.15 level if I put 0.15 in for the alpha value.
So if you change another one, I just want to see it is very sensitive or not.
Yeah, that's a good question. So if I make this 0.005, right, yeah, I get almost nothing, because now, right, it's just about impossible to reject independence. So everything looks independent of everything else at 0.005. But now you're well, in the theory, right, as the sample size increases, I have to gradually reduce the p-value, all right, to be asymptotically reliable about actually my statistical decisions. But the theory has 2 parts. One part is, if we assume that your independence decisions are correct, so if you're an oracle, and I can ask you what's really independent of what in the population, and you always tell me the correct answer, then we know the reliability of the algorithms. But the statistical performance of the algorithms depends upon how accurate each of those statistical tests is, and it's a complicated joint question, which there's no theoretical answer to. So we've done lots of simulations and showed that if you have this many variables and you have this kind of model generating the data, and you have, right, this kind of sparsity or complexity in the model that generates the data, this is the kind of reliability you'll get about adjacency and orientation. But the question of how reliable the thing is actually interesting and complicated.
So this basically where we put the subjective kind of our guess into the model? Or?
No, there's lots of ways to actually handle this. And in this algorithm, which you have to find an alpha value for, right, you have to pick some value that makes some sense according to the simulation studies we've done for this sample size and this number of variables.
as kind of guidelines for how many variables, how much different
Yes,
number you can put.
yes, and I can point you to where those are.
Okay, thank you.
Okay. Now, if I actually want to take a model and estimate it, right, I have to come and take this model and put it into an acyclic graph, right? And so to do that, oh no, I can't do that for this one. Okay, that's all I'm going to do for now. I'll come back to the part where we actually estimate the models in a few minutes. So let me stop and now ask you guys to get the program up and running, to load the TW data into the data file, and to perform one multiple regression so you can do what we did right before we did the search. And we'll walk around and help you if you have any problems. Okay? So let's take about 5 or 10 minutes to do this.
Yeah, go back to the slide, show where to
Okay, so I've now finished the motivation insofar as it's going to go, and I want to move into representing causal structures, both very, very crucially in a theoretical sense, and then with the program that you're now successfully using. So the first thing to talk about is what's a causal graph and how does it represent, and then we're going to talk about parametric models, which actually allow you to connect to probability distributions and data, and then finally we'll go to how do you estimate models and how do you search for them. So the basic representational object that we use in this whole domain, right, is the simplest possible object you can imagine. It's just a directed graph, where the edges in the graph, right, represent direct causal relations, and the boxes or the nodes in the graph represent random variables. And so every time we draw a graph, if we're claiming that we are representing something about the world, then what we're saying is that each variable in the graph that has an edge into any other variable is a direct cause of that variable relative to the variables that we've put in the model. And that's important to understand because there really is no such thing as an absolute notion of direct causation because it's entirely relative to what you actually are using as a set of variables to talk about. So I think everybody would agree that years of education is a direct cause of income if all I'm talking about is education and income. But if I add this other thing, like what are all the skills that one could get from education? What's all the knowledge, right? Including network social knowledge, anything you might get from education, right, that would help you make money, right? Then now the relationship between years of education and income is not direct, it's indirect, but it's via, right, skills and knowledge. So the causal graph is a representation of the direct causal relationships relative to a set of variables you're given. Now, we insist representationally on some things but not others. And one of the things that's confusing when people first learn this, but really should be specified clearly, is when you write down a causal graph and you claim to me that it's a true representation of reality, you are not claiming to me that it's a complete representation. You can't be expected to list every cause of every variable. So if I say years of education causes skills and knowledge causes income, right, I don't mean that there's nothing else that causes income besides skills and knowledge. There is, right? There's luck, there's all sorts of other environmental factors that might influence it. So it's perfectly fine to write down a graph and say, I'm leaving out, right, what are called the omitted causes, right, of each of the variables that are not discussed or are not represented. But what's not okay is omitted common causes. So when I write down a graph and I say it's an accurate representation, I am also claiming that for every pair of variables, right, there's no omitted common cause of that pair. And we say such models are common cause complete or causally sufficient. Now I want to make sure I distinguish for you between the idea in representing the world with a graph you write down, as opposed to the idea of I'm now going to try to infer from data what might be producing the data, right? And I've measured only certain variables in my data and not all of the variables that might be out there, including common causes, right? So when I'm doing inference about the causal structure, I do not have to assume that the variables I've measured are common cause complete. In fact, we have algorithms specifically tailored to that situation, which is the realistic situation you're in, especially in social science. But when I'm representing, I do have to actually, I have to claim that my model, right, is representing accurately by saying it's common cause complete. Yeah.
So omitted common causes are important because in science, a lot of times because we usually don't know if there's really any common cause or not.
Right.
So how do we, like you said, how do we track it along? We just assume it's not there or what?
No, there are some algorithms, right, that you can apply that require you to assume they're not there. But there are other algorithms we've developed that do not require that assumption. And we'll find an output that represents models including models that have omitted common causes, and in some cases will tell you what pair of variables have. Yeah, and I'm going to get to that in some detail, because I think that's one of the more interesting parts of this whole project. But I just want to make sure that representationally we're all clear. Okay, so as I've talked about before, the interventional perspective is key. And so when you're talking about causal structures, part of what you need to represent is interventions, right? So there's lots of different kinds of interventions one might do. The first kind that we usually talk about are what we call ideal interventions. And they're the kind of interventions that randomized clinical trials purport to implement, which is, right, we're going to assign the value of whether or not you take a drug or not, and it's going to be a completely deterministic intervention, so that if we assign you to take the drug, right, we don't have any doubt that that's what you'll do, and if we assign you to take the placebo, that's what you'll do, etc. So the key feature of modeling interventions and how they interact with causation, right, is that interventions can change the causal structure that you begin with, right, and they change it in a specific way, right? So if I'm looking at a system as simple as the room temperature is going to cause whether or not you wear a sweater, right, which it does, I presume, right, and then I say I'm going to actually do a randomized trial in which I flip a coin, and if it comes up heads, right, you're going to take off your sweater, and if it comes up tails, you're going to put on a sweater, right? You have no choice. That's the experimental regime, right? I got Clark Lemar outside, and if you fail to comply, he comes in and makes you do what he wants, and that's the story. And then we ask, well, what's, if any, the modification to this system? Well, the modification is that any influence that room temperature might have had previously has been annihilated, right? We have determined your sweater wearing behavior, right, not the room temperature and your own comfort, right? And that's what it looks like. So the post-experimental system is different than the pre-experimental system. Now, take the same system and consider a different experiment where I don't intervene on the sweater wearing behavior, I intervene on the room temperature, right? So I put a partition up here, and this guy, right, on this side of the room, I randomly assign 50 degrees, right, and that side 85 or 90 degrees, and then I observe what happens. And in fact, in that post-experimental system, I will not annihilate this causal arrow. I will change the value of the room temperature as my intervention, but the effect that the room temperature has on sweaters will not be annihilated. You will still wear the sweater if you're cold and take it off if you're hot, right? And the only thing that's going to change is this value, not this relationship. So the asymmetry of causation is easy to express and capture by the asymmetry of how the system responds to an intervention that's ideal in this way, right? And this is sort of one of the fundamental representational gambits, as you are, of this whole field, right? So we can model very generally the way a system responds to intervention, even for interventions that are not what we call surgical or hard or ideal, right? By saying, if I give you a pre-intervention graph, so education causes income and income causes taxes, right? And I intervene on income, right? If I do a hard intervention or a surgical intervention or an ideal, like I've just talked about, for example, I flip a coin, and if it comes up heads, you have an income of $100,000. If it comes up tails, you have an income of 50. Nothing else matters in terms of the determinants of your income, right? Then education's influence annihilated, right? But the income, the effective income on taxes remains the same. You still have to pay taxes no matter how you got the income. Okay, but now there's other kinds of interventions I could model. and what we call soft interventions, and instrumental variables can be modeled in this way. So if I, for example, flip a coin and it comes up heads, and instead of assigning you 100,000, I give you a bonus of 20,000. And if it comes up tails, I give you a bonus of 50,000. Then the way I represent this system, right, is I keep these edges intact because your income is still dependent causally on the education you brought to the table, but it's also now dependent on the result of the intervention I did, whether I throw you a $20,000 or a $50,000 bonus. So I can model both perfectly reasonably, and in some sense, what I can learn about a system once I know what intervention I'm making varies according to the kind of intervention. And there's a whole subfield, right, that's emerged from this about studying, right, interventional types, sequences of interventions, right, that you can use to actually learn a lot about the structure. One of our former students, Frederick Eberhardt, has done really nice work in that area. Okay, so now I want to go back into the program, and I'm going to demonstrate it first and ask you to do it. I want you to get clear that the first thing that you're doing when you actually build a causal model is doing nothing that has numbers or probability or quantities associated with it. It's a purely qualitative object. It's just a graph, right? So if I go into Tetrad and I go to this file menu and I say start a new session, right? If I go to the window, I still have these other sessions, some of which you haven't seen. But the workspace is blank, and I get to do a new thing, and then I want you to click on the graph, put it on the workbench, click on it again. So I want to put two graphs on there, and I can fill them by double-clicking on them. And then I have several different kinds of graphs to choose from, right? Let's choose directed acyclic graph, which is the simplest part of the, the theory, and then say OK. And then it says, well, do you want to do it manually? Or do you want to do it randomly, because Joe Ramsey does all these simulation studies all the time, so he's always generating random graphs, but we are going to do things manually. So you are left now with the graph editor. And in the graph editor, you can add variables that have boxes, which are measured variables, and you can add variables that have ovals that are unmeasured or latent variables. So they behave exactly the same under the hood. The difference is the measured variables you will get data on, and the latent variables you will not. So it's just like you were in the world generating data, and the scientist is out there, and the scientist didn't measure everything that's going on, they only measured some things. Right? So for now, just use the measured variables. If you click on that, and then you click anywhere in here, any number of times, it will deposit variables. You can rename them by double-clicking on the variables, and I can say education, income, etc. Happiness. And then I can choose this arrow thing and then click on the cause, drag, let it go on the effect, and then if you go to this button, which is the move the objects around, the edges will follow you so you can make the graphs pretty and lay them out as you want to. Okay? So all I want you to do now, so I want to stress that what I've built, right, has meaning insofar as the arrows go one way as opposed to the other, and that's going to translate later into a particular kind of behavior of the statistical model that we're going to actually generate data from and then estimate. But now I want you to do is I want you to build two graphs, one with 3 variables and one with 5, and then add a latent to the 5 variable graph. And then when you finish with this, you say save. And then you can see that the graph thing that I've filled is blue, and the graph thing I haven't filled is gray, right, to indicate that it's not been populated yet. And anytime you can attach a note, right, saying this is education, Inc., happy, right, and do what you will, okay? So go ahead, take 30 seconds, a minute, and go ahead and build a couple of graphs, and then stop, and then we're going to go into how to take those graphs and turn them into statistical models, right, by parameterizing them and then actually putting numbers in for the parameters. Lots of different ways as a statistical model, but have consequences because of its qualitative structure, right? So we have at least two that are easy to manipulate in the program. One's called a Bayes parametric model, and one is called the structural equation model, parametric model. One has primarily all discrete valued variables, and the other has all continuous variables with linear functions connected. So now I'm going to get into, right, those two kinds of parametric models and make you build, right, one of each, so you have full familiarity with what those actually are. Because this is where we really get into what are the objects that we're trying to discover, right, on the other end of the field. Okay, so once we actually put a parametric model in place that actually interprets the graph, that doesn't have numbers in for the parameters. It's just a parametric family that we're saying this graph is going to interpret, and then putting actual numbers in for the parameters, like the actual values of the edge coefficients or the actual values of the probabilities. That takes us into what we call an instantiated model, right? So that is just the difference between an algebraic coefficient, beta, and a numerical real-valued coefficient, right, 0.3. So there's two kinds of parametric models. One are called causal Bayes networks, or, right, just Bayes networks. And along with the graph, one has to parametrically decide what values each of the variables might take on. So if I say my variable is smoking, this represents that the variable could take on a 0 or a 1. It's a binary variable, right? Same thing for yellow fingers and lung cancer. And the basic connection between the parametric model and the probability distribution in a Bayes network is that the joint distribution factors according to the causal graph, right? So there's a general expression of it more concretely. If I say, well, what's the probability of any possible state of the values of the variables smoking, yellowed fingers, and lung cancer, right? I can write that as the product of the marginal, right, of smoking, the conditional yellowed fingers on smoking, yellowed fingers on its, and lung cancer on its cause, right? So I'm writing each variable in the factored expression, right, as a conditional probability condition on its causal parents in the graph, and only its causal parents, okay? So that allows us to parameterize the model, right? In this case, if they're all variables, they're binary with 5 parameters, right? So the probability that the smoking variable is 0 is theta 1, and the probability that it's equal to 1 is 1 minus theta 1, so I only need one parameter to, right, express the marginal distribution over smoking. For the yellowed fingers, right, I need 2 parameters. One for the smoking is equal to 0, and one for the smoking is equal to 1. So in here I have the yellowed finger, 0 or 1, given smoking is 0, that's theta 2. Here's yellowed finger, 0 or 1, giving smoking is equal. So these 4 rows define the conditional value, conditional table of yellowed fingers on smoking, and I need 2 parameters to express those rows. Same thing here. So I have, this is a 5-parameter model. Okay. Now, if it turns out, right, that I just expressed this joint arbitrarily, I would need 7 parameters to express this joint. And what's interesting about these models and how they came about, in some sense, was that when you have a graph that's sparse, that means not all the edges are present, right? It implies independence relations, which allows you to express the joint distribution much more compactly, with fewer number of parameters. The more sparse the graph, the more independence relations. The more independence relations, the fewer number of parameters one needs to express the joint distribution. In fact, what happened early on in the 80s, a little bit of historical reconstruction, but not too much, is that Judea Pearl and lots of his colleagues were looking for very efficient ways to have robots represent the world using probability, right? And they realized that if you could have independence, you could store much bigger probability distributions more efficiently, and then you could update your distributions much more efficiently using that independence structure. And so these graphs, right, became a very efficient way to compute the independence relations, right, that were entailed to hold in the distribution. And so by building a graph, you could build an independence structure and therefore be efficient in how you stored and updated your probabilistic information. Okay, so now what I want to go through and demo is to build a parametric and an instantiated model, right, with discrete variables. Okay, so let me go ahead and do that, and then ask you to do it with your program. So if I'm going to take this graph, which is just education causes income causes happiness, I'd say go into the workbench and select this parametric model, click on it, and then drag from the graph into the parametric model, which forces the parametric model to interpret that graph. And then it's in gray because it hasn't figured out which parametric model. So if I double click on it, it says, okay, which ones do you want? Structural equation model, Bayes, and a generalized SEM parametric model means you can express any function, well, pretty much any function, connecting the causes to their effects. You can use linear functions, you can use quadratic functions, exponentials, logs, tangents, etc., etc. But the Bayes parametric model is special, right? I'm going to set it up manually. So what I have to do to specify a Bayes parametric model is very, very little. All I have to do is for each variable, and this one's going to tell me in yellow which variable I'm now working on, is say how many categories that variable takes on, what are its values. So education is really not 0, 1. Let's give it a little more structure, right? Let's say 3 categories, and make the first one high school, second one college, and the third one grad. Okay?
Excuse me.
Yeah.
This one we can only use the categorical variables. Can we use the continuous variables?
Not in this parametric model.
No.
That would be in the structural equation model
Yes.
or the generalized structural equation model. So in this one, you're forced to use all discrete valued variables. And what we're working on, and really it really needs to happen, is a parametric family in which you can use mixed, some continuous, some discrete, because that's really what we typically.
That's the generalized ones.
Yeah.
Okay.
Yeah. Okay, so that's what I've done now for education. Income, right? I can go to this presets button and say, oh, here's a couple of ones I could use presets. So let's do low, high. And happiness, let's just do low, medium, high. So now I have all the information I need to specify a parametric model. That's it. Done. Now, if I want to put numbers in for those parameters, I go to the instantiated model button, attach that, double click on it, and then it says, yeah, Bayes instantiated model. I'll build it manually. Now I have to put in the probabilities. Okay, and here's where I get to, right, at the very detailed probabilistic level, play God. So we're building the truth, right, and from that truth we're going to generate simulated data, and then from that simulated data we're going to apply algorithms that actually tell us what we think is going on behind the scenes, and we can check, right, with what really is going on behind the scenes. Okay. So I have to assign a probability for one, right, population, this population, of how likely it is that you only have a high school education. So maybe it's 0.5. And maybe if I hit tab, I get to the next box. This is 0.3. And if I hit the tab again, it fills in the last one because it knows that they have to add up to 1. It's a genius program. Because I can't do that mathematics usually. Okay. So that's the easy case because this is the exogenous variable, so specifying its distribution, right, is simple. Okay? Now the income one is more complicated. If I click on the income, the table that appears has 3 rows. Income is either low or high, and I've got to specify its distribution for each possible value that its immediate cause can take on. So what is the distribution of low and high income when you're only having high school education? Well, it's very likely you'll have a low income. In college, it's a lot more likely you'll have a high income. And in graduate, don't we wish, that it's even 90% likely you'll have a high income, where high income might be something reasonable like, $60,000 a year. Okay? So what we've done by showing how these rows change from one row to the other is we have parameterized and instantiated and expressed the causal relationship between education and income according to this model. We don't have to do it this way, we could do it in another. Happiness, how does this depend on income, right? Well, we could say, we could say anything we want here. We could say, okay, the probability of happiness, right, is such, and right? If you're high, it's a little bit lower, let's say. So the influence of income and happiness is quite weak according to this particular model. But you can do anything you want. Okay? So go ahead and take your 3-variable model, put your parametric model in place, put your instantiated model below that, and go ahead and actually fill in numbers. So you have built, right, a full instantiated model. And then when you finish, you can take data and attach it to the workbench. And when I put an arrow from the instantiated model to the data, what I'm saying is that if I decide to draw data, I'm going to pseudo-random sample that data from the population that this instantiated model defines. Because now the instantiated model, right, contains a full probability distribution over the variables, right? And then from that distribution, I can sample data, and then I can find, right, what the data tells me with algorithms later on. So to do that, I just double-click on the data, and all it asks me is, well, what sample size you like? And the default for me is 100,000, so I'll go a little smaller than that. I'll go 1,000. And there it is, and so I've now got 100,000, I've got 1,000 data points sampled from this distribution. And if I want, I could do another data set, do this one of sample size 50. So now I have 2 data sets drawn from the same population. I could have 2 instantiated models that are different parameterizations of the same parametric model, etc., etc., etc. So understanding this column, graph to PM to IM to data, you get the theory, at least representationally. Okay? And then we're going to actually go the other way and move from data back to theory. Starting with a causal graph and choosing a different parametric family, right, than discrete values, I can choose now to deal with continuous variables, right, or at least approximately continuous variables, and connect them parametrically in a different way. So if I take a causal graph like this, where I take education to cause income, it also causes longevity, right, I build a set of what are called structural equations. So for each variable v, right, I build that equation, right, as a function of its immediate causes, plus this little thing that's called an error or a noise term, and which represents all the other omitted causes that I didn't model, and their joint aggregate effect. Okay, so in econometrics, this is called the error term. It's called other things in different domains. You can think of it as all the unmodeled or unexpressed other causes, right, that I haven't put in my model. Now, this function, x, right, and that's an assignment operator to indicate it's causal, right, can be any function, right, and we still are in the framework of graphical causal models. But the usual setting, or the most simple setting, is using a linear function. So every effect is a linear combination of its causes plus some error, right? And that's actually quite a bit more powerful than you would think, because you can transform the variables and achieve an approximate linear form, and you can include interaction terms and stay within that family and still have quite a lot of expressive power. But for lots of reasons, you do want to be able to go beyond that. So besides the structural equations, we have to actually express some exogenous distribution, which is a joint distribution over those error or noise terms. And I'll get to that in a minute. So here's an example. If I have this graph, right, what I usually do is build what's called a path diagram. The path diagram has these coefficients that represent the linear, right, coefficient in the relationship, right, between that variable and its causes. And these error terms are expressed as unboxed, right, inputs into each variable, and they have their own distribution. So here are my equations, right, according to that model, and I can do that all in matrix algebra, and I can build, right, a whole theory of linear models with matrix representation, and it's very handy and very powerful, right? We're not going to get into any of that at all. And I have to specify something about the exogenous distribution, because the place that these models get probability, right, stochasticity, is by saying these error terms have a distribution. And the typical strategy in most social science cases is to assume that they're Gaussian, normally distributed variables, right, with a mean of 0, which is without loss of generality perfectly fine. Okay? Assuming they're Gaussian is a much bigger assumption, and it turns out an interesting, really interesting, cool development in this field. If you have a linear set of models, but with non-Gaussian errors, what you can learn about the model is much, much more powerful. Right? It turns out you can learn almost everything you need to about the model if you have a big data set.
Yeah, how do you deal with intercept terms here? Or either if you want them or if you don't want them?
That's up to you. So it makes no difference to the connection between the causal structure and the data to have an intercept or not, because we're only looking at covariance, right, as our connection to the data. So the covariance of the correlation is unaffected by the intercept. I'm not going to go into that. Let's just actually go ahead and let me build that and ask you to build it, and then I'm going to go into estimation and model fit, which I need to finish before we do a break. So I want to do the same thing we did before, but now use a different parametric family. And I want to actually have you, and I'm going to show you how to do that first. So what I can do here is take the same model I had before, the graph, right? And then choose a different parametric model, not the Bayes one, but the SEM parametric model. And there's nothing to do to build the SEM parametric model. The coefficients, right, are given algebraic, right, beta 1, beta 2 values, and in fact there are parameters, there are error terms that I want to show them, right, they are put into the graph as well. So the linear form is nice. You don't have to do anything to actually specify. You don't have to say how many variable values a variable has. You don't have to say what coefficients. It's given and calculated for you. What you do have to do is put in values. And so if I say, give me an instantiated model, and say a SEM-instantiated model, it'll actually pick those coefficients from a distribution for you, right? And then you can change them. And that makes it, because if the number of variables is big, it's just a big pain putting all those values in. So I'm just going to put them in there randomly. And now I'm going to hide the error terms for a minute. So I can see that this is negative 0.672, and if I want to change it, let's say to positive 0.5, I just type that in, click OK, and now I've changed the linear coefficient in that model, and that comprises 1/2 of the parameters of a linear structural equation model. So let's say I make this 0.6, right? And now if I want to, I can go into the tabular editor, and I can see all the coefficients here. Here's an edge from education to income. Its coefficient value is 0.5. Here's an edge from income to happiness. Its coefficient is 0.6. And then each of the variables has a standard deviation and a mean. And so if I want to actually change the variable, the error term and its distribution, I can go in here, click on that guy, make him 1. Etc., etc. And now I have built an instantiated model, right, for a linear form for the same graph. And now if I get data from that guy, give me 1,000 data sets. Now look at the data and the difference. So here is 1,000 data points on the left from the discrete Bayes net parametric interpretation of this graph, education, income, and happiness. And here's a data set of the same size from the continuous structural equation model parameterization of this same graph. So these data sets, right, share the same graph that generated them, but they're different parametric interpretations of that graph. Okay?
How did the system assign the coefficients initially?
It chooses from a random distribution between like 0.5 and 1.5. And then it randomizes whether they're negative or positive. What?
Is it random number generated?
Yeah. Yeah. And we could change that, so you have to put them in by yourself, like the I don't know why we decided that. Joe, do you remember why we decided that? Okay. So Go ahead and parameterize your model as a SEM, and then change the linear coefficients and change at least one of the error standard deviations. And that should only take you about 30 seconds to a minute. And I want to come back and I want to get to estimation and model fit, and then we'll take a break. Right, now we're going to start back the other way. So you've generated data, hopefully from a discrete and a continuous variable model. And now we're going to start moving back to the other side of this coin. Now you're a scientist and you need to try to infer something about what's the world like. Okay. So we're still going to be working with a known truth, so we can compare what we get from our inferences to what the truth is, right? And understand things a little better. And the first thing that everybody typically does with a statistical model that they specify is estimate the parameters of that model. Okay? So when you do a regression, you're estimating coefficient parameters. And when you do a structural equation model, you're estimating the parameters of the structural equation model. Same thing for a Bayes net. Where do you think, if this is the estimator, right, I should put inputs into the estimator from these other nodes?
Data.
You got to have data. So there's got to be data that goes into the estimator. Is that enough? Should I just estimate the model now? So this model, it doesn't know anything behind data. It only has the data. So can you estimate just from data? You need a model, right? You can't estimate nothing. You got to estimate what? So what goes into the estimator besides the data? What, the graph? The parametric model. It's not the graph. The graph has no parameters. It's not the IM. The IM has numerical parameters already assigned. The parametric model, right, is the empty hull, right, of algebraic parameters. And when you estimate, you are finding the values to put in for those parameters that minimizes some loss function or maximizes the likelihood of the data. So this alone, I think, is informative about what's happening in statistical causal models. If you understand that, right, you'll understand a little bit about what's happening. So in this particular case, right, I've taken a graph that's just x1 causing x3, x2 causing x3, x2 causing x4, and I want you to build the same, but not right now. And I've parameterized it as a SEM. And then I've done the coefficients to be very simple, 0.5, 0.6, 0.7, right, and the tabular editor, they all have standard deviations of 1. And now I say, okay, what's the estimator? Just double click it, and up it pops. And it looks just like an instantiated model. And what it is, right? So on the left, I have the true instantiated model. This is what I generated data from, but only 1,000 data points. So the data are going to be variable, right? And so when I estimate the parameters of the model, the estimates are not going to be exactly the truth, but they're going to be, hopefully, reasonably close. So the estimate of the x1, x3 coefficient is 0.4788, and the estimate is very close to the truth, which is 0.5. Now, what do I usually do, which is I go to, right, the parameter and I say, well, what are its standard error for estimation, what are its p-values, et cetera, et cetera. And I find out that they are, right, 0, 0, 0. So these estimates are all what are called highly significant, right? But you see that I've taken a model, I've estimated its parameters, and the parameters are quite close to the true causal parameters, which I specified, right, by playing God and building a model myself. Okay? Now.
So far,
Yeah.
what does estimator give you that the parametric model did not?
So the parametric model has algebraic parameters. They don't have real values. And when I estimate the model, I'm picking real values to minimize the difference between what that model implies about the data and what the data is. I'm trying to get as close to that data as I possibly can. So it's like, if my parametric model is I have a fair coin, not a fair coin, if I have a coin and the only thing is a binomial parameter on the probability of heads, right, that's the parameter to be estimated. Do 50 coin flips, right? If I get 25 heads, the estimate will be 0.5. If I get 30 heads, it might be 0.6, right?
But, I mean,
Yes, I'm getting to that. So I'm just showing you that if I know the truth, I should be able to compare the estimate to the truth. Okay,
So in essence, you're doing toy experiments to show that the methodology works.
correct.
Okay.
This is like, oh, I'm still calibrating the instruments so far. Got it.
But in this case,
But now, right now, I'm going to get to the fun. So just give me a minute. Okay. So I've estimated, right, the true parametric model. And what I'm getting, right, when I estimate those parameters versus the fit of the model, right, is a different thing. So if I go to the program again, I can say in the, right, estimated model, what are the model statistics? And I get the degrees of freedom, which corresponds essentially to how many constraints that model entails on the covariance matrix or the probability distribution. The chi-square is a measure of how much deviation there is between the estimated model and the data I measured. And the p-value is the probability on the assumption the model is true that I'd see that much deviation or more. So p-value of 0.1264 means this model can't be rejected. The good thing is it was a true model, I estimate. But it doesn't have to have a probability of 1 or a probability of 0.9. It's just that this data set happens to be reasonably far away from the actual perfect truth, so it's not a really high p-value. Now, if I now say what's the p-value of the parameter, the p-value is the probability, the estimated value, right, in this case is, right, I'm looking at the x1, x3 coefficient, and I estimated it to be, right, 0.4788. The estimated value that is bigger than or equal to 0.4788, given the true parameter was 0, and the rest of the model is correctly specified. And I want to make really, really big emphasis on that the only thing that you get out of a p-value is it's conditional on the null hypothesis for that parameter and that everything else in the model is true. Right? So the meaning of these p-values, right, is not what you usually take them to be in a causal context. So in this case, if I ask what's the, right, the model fit p-value, the null is that the model is correctly specified, and that the p-value is now the probability, right, that deviation between the estimated covariance matrix and the real one that I measured, right, chi-square is the measure of that deviance, will be bigger than what I actually found it to be given the model was correctly specified. So the logic is opposite, right? In the coefficient estimate, the logic is assume it's 0, and we want to reject it 0 to assert that it's really there. In the model case, I'm going to assume the model is true, and if I can't reject the model as true, I assume it's unrejectable. Not that it's true, but that it's unrejectable. So the logic is a little different, okay? But you do want to have a model that fits the data if you can find one. Yeah?
So what's the range of this p-value for each kind of like model and also the
0 to 1, right? So, and the distribution of that p-value, right, is determined by the sampling distribution. So that's where you bring in probability theory and really get the p-value computed.
So when you say that if the model is not rejected, then the proper statement would be the data do not suffice to reject the model.
Correct.
Okay.
That's correct, yeah.
When you say the rest of the model is correct, do you mean the model is specified correctly, or do you mean the parameters, other parameters are estimated correct?
Both.
Both.
So more importantly, the model is specified correctly causally. Okay, now I'm going to show you something that I want you to do because this is where the rubber really hits the road. So if I'm going to go to this and I'm going to say, okay, estimation 2. So what I've done here is this. I've taken this graph, right, which is the one I've shown you here. x1 and x2 cause x3 and x2 causes x4, right? I have generated data from that graph and I've estimated it. So I've got this estimator here. And in the estimator, I see that I've got a p-value of 0.124 right, which is sufficient to say the model can't be rejected from the data. Now, what I've done is I've taken this graph, and in one case, I've flipped one of the edges. So the true graph has, right, this structure, and this graph is the same except for I've flipped the x2 to x4 edge. It's causally a different model. And I've done it again, but this time I've left these two edges the same, and I've flipped the x3, x1 edge. So in each of these cases, I flipped one edge from the truth. Okay? And then what I did was, I said, okay, given those two one-flip differences, I built the parametric model, and I estimated those model from the same data, right? And now, I want to look at these estimators and see what I can tell. Okay, so there is the model in which I flipped the x4, x2 edge, and here is the model in which I flipped the x1, x3 edge. Okay? Let's look at the coefficients. Coefficient 0.47, p-value is 0, it looks highly significant. 0.62, p-value is 0. 0.5, p-value is 0. Very highly significant coefficients individually. 0.28, 0.6, they're all highly significant coefficient estimates. There's nothing in the coefficient estimate inference tables that would tell you anything about the causal information you're getting in those parameters. Okay? You don't know what's causing what and what level it's causing what from these coefficient tests, which is all you do usually when you do regression. So let's go to the model fit. Okay, this model is different than the true one. What do you notice about the model fit? It's precisely and perfectly the same. There's not a single difference. The probability of 0.1264, the chi-square of 0.5 is exactly the same as the true graph, parameterized as a SEM and then estimated in every detail. Now, here's the one where I flipped x1, x3. Now the p-value is 1.24, right, with 8 zeros in front of it. So it's as rejectable as you could be. So in one case, I flipped an edge, and I have a completely equivalent model. There's no way to tell it from the truth at all. In the other case, I flipped one edge, and it's completely crap. It fits 0 data that I've measured. So I can tell, I can reject it like at 8 levels of significance. So what we can offer you now is I can explain to you easily and clearly, right, how to predict which one edge flip would preserve equivalence and which one edge flip would leave equivalence. And all you can really tell from data is the set of equivalence models, right, which all fit the same. But you can't tell within that equivalence class which is which. And so what we have to know is what are all the features of the models that are shared within the equivalence class and what's different when you go outside the equivalence class. And that's all we can know causally. That's what the search will give us. Okay? So what I want you to do now is go and generate, right, this particular structure, right, by taking by taking the SEM, building it, and doing this, and then we'll take a break, and I'll come back and I'll go into, right, how the search actually works. So I want to begin this next section by showing you another example of a real data set, and then have you later on, when we finish, go to work on this data set, applying the search, and try to find a model that actually fits the data. So a few years back, there was a student here, Cynthia Kreider, who was looking into what are the factors that influence people to charitably give, to donate. And she did an experiment in which she randomly assigned people to 2 conditions, one of which tried to get them to be very specific about whether they could imagine who they were donating money to, what impact it was going to have, and make it so that the target were people they were very sympathetic to. and the other less so. So on 94 people, she had a condition that was randomly assigned experimentally. She had a measure of what she called imaginability, how concrete the scenario was. She had a measure of sympathy, how much sympathy did you feel for the people you were potentially donating to. Impact, how much impact do you think you're going to have when you give money to these people. And then actually in the end, you could actually donate money. You were given a little seed from the experimenter and you could donate all of it back or some of it back or more, and that was all recorded. So the theoretical hypothesis that we were offered was the tangibility condition was exogenous, right? It was randomly assigned, and that it would directly affect imaginability, and imaginability would actually impact sympathy, and then they would both affect amount donated. So this was the theoretical hypothesis. So in Tetrad, to estimate this kind of a model, you'd take data, right, and again, load the data, right, from some hard disk location. And in this case, I have raw data, not covariance data. So instead of covariance data here, I have to say tabular data. Otherwise, I say load, save, and now I have my data in there, and I can go to work on that data. And the first thing I want to do is check to see if the hypothesis, right, that they've offered me as a theory, right, fits the data. And then later check to see if there are alternatives that fit the data as well or better, that are different causally. Okay, so to do that, I have to build a graph. And in order to make the variables in the graph the same as the variables in the data, I can drag the data as an arrow into the graph, and it will begin for you with the variables that are already in the data set, and that connection is made automatically for you. And that can be a big pain in the butt if you don't have that connection. Then you got it, because you have to spell them exactly the same, etc. Okay? So now I'm going to arrange these in the same way that I did before. There's my graph. Save it. Put a parametric model. SEM is okay. Put an estimator. Okay, get good coefficients. P.014, almost significant at 0.01. Very significant, significant. Marginally significant, significant. Am I done? What should I do? Model statistics. What's the fit? Real bad. So this is exactly the opposite of the usual p-value test. Low p-values mean reject the model. So this model, if it was true, right, the probability of seeing that big a deviation between the implied and the measured covariance matrix is, right, 0.00000000000053656, something like that, right? So it's extremely unlikely that we'd see this kind of data if this was a true model, right? The authors were they were crestfallen, they were upset. So I said, but that's not all we can do with Tetrad. We can find you a better model. Okay, so that's what we're going to move to now. Okay. 10-minute break is over.
But I have a question.
Yeah.
It makes me uncomfortable to work with data that I haven't actually looked at and seen histogram. So is there a facility to do that?
Yes, in the data you can look at histograms, you can do Q plots,
Okay.
right? And I should tell you that
Double entry and stuff?
yes.
Okay.
I should also tell you that in Tetrad there's the facility that you can take any data set that you simulate or you otherwise do, and then you can say File, save the data onto the workbench, and then you can analyze with any other program you like.
Yeah.
R, Stata, Minitab.
And the histogram and stuff is under tools? Is it?
Yes.
Okay, wonderful.
So I do a histogram, I'd say, okay, here's the experimental condition, it's 50-50. Okay?
All right, thank you.
Okay, so when I usually do model search, I usually teach what are the bridge principles between causal structure and probability that actually allow us to do search, and that involves what's called the Markov assumption, the faithfulness assumption, and it leads us to, in some sense, the key to the causal universe, which is deseparation, which stands for dependence separation, which is a graphical criterion for when two variables are independent, conditional on another set of variables, right, in any distribution that graph could produce. But we're not going to cover any of that right now, because that's hard and takes a long time. I'll get back to it if we have time. The odds of that are almost zero. But what I want to really do is get you to what you need to actually run the program and be able to play with it, so you can, right, produce these things by yourself and then test your knowledge of deseparation, etc. So what we're doing search, what's essentially going on is we have data, and we're looking in one set of search algorithms for constraints in the data that hold that will tell us something about the set of models that could have produced that data. So we have raw data, we have to do some inference about what kind of constraints we think hold in the population. So this is a completely regular, decent, God-fearing statistical test, right? We could do a statistical decision out of Bayesian, we could do it as a frequentist, it doesn't matter, right? We need to make decisions about things that are in the population true, and in this case I'm using independence and conditional independence, because that is the simplest, most classical constraint that we use in this whole thing. So x1 is independent of x3, conditional on x2, right? This means that the probability, right, of x1 and x2 jointly factors, right? And this means that x1 and x2 factors into x1 given x3, x2. So that's what independent means, and the quantifier should be taken to be universal for all values of x1, 2, and 3. Once we have those constraints, we then apply a discovery algorithm which says, what are the equivalence class of causal graphs that could have produced those constraints via deseparation of the causal Markov assumption, right? So in this case, x1 is independent of x3 given x2. If that's the only constraint we observe in the data, then these are the three graphs that could have produced that constraint by their structure, right? And assuming that there are no latent common causes that I've left out. So these are very strong assumptions that I've made in this case just to illustrate, right, what you could do if you had those kind of assumptions. Now, any good search algorithm ought to allow you to include, as a theorist, background knowledge you have about the system you're working in, right? Because you have a lot of that in many cases. So in this case, if I happen to know that x2 is prior in time x3, and I'm going to assume that variables that are prior in time can't be caused by variables later in time, right? Then I can cut one of the members of the equivalence class and say, we're not even going to search for it because it violates our background knowledge that we've put in. Okay? And I'm going to show you how to include background knowledge as part of the search. Now, that's a constraint-based search which looks at individual constraints, independence constraints, and then moves through the space of models that could have produced that set of constraints sequentially. Each time it sees a constraint, it cuts down the search space dramatically, and so it's extremely efficient. But if you make errors in your statistical decisions early on in the process, that could ramify into lots of errors later on because you won't even test the right stuff. Another kind of search is called a scoring search. It takes data, and then it takes different models, and for each model computes a global score of how that model fits the data, which is usually a simultaneous comparison of all the constraints it implies simultaneously to see whether they, right, fit the data as a whole. And what you can really do in this case is not score, or you shouldn't really score single models, you should score equivalence classes, because every model in the equivalence class will have the same score. And so what you're really searching for is equivalence classes. Okay? And again, if you have background knowledge, you can cut out every member of the equivalence class that violates that background knowledge. Now, we have lots of different kinds of equivalence classes we've looked at, and the two that I'll sort of discuss today are called patterns and PAGs, partial ancestral graphs. Patterns are the simplest kind of equivalence class, and they include all the causal structures, right, that leave out latent common causes. So if you're willing to make that assumption that the variables you've measured are common cause complete, that you have measured every confounder and put it into your data, right, then you can search for a pattern, because it doesn't allow any latent variable common cause models to be considered in the search. But if you want to allow latent common causes, then you can search for PAGs with a different set of algorithms, right? And I'll get to that in a minute. First, I just want to go over pattern search and then get you to the point where you can do it, and then we'll be pretty far along. Okay, so what is a pattern and what does it actually tell us? Well, here's an example on the right of a pattern. It kind of looks like a causal graph, except for this little edge on top, which is undirected. And so the possible edges in a pattern are the null edge, the undirected edge, and the fully directed edge, and that's the only thing you can see in a pattern. And there's an example. And what the edges mean is, if I have a null edge in the pattern, it means that x1 and x2 are not adjacent. x1 is not a direct cause of x2, x2 is not a direct cause of x1 in every member of the equivalence class. There's a fully arrow means x1 is a direct cause of x2 in every member of the equivalence class, and the undirected arrow means x1 is a direct cause of x2 in some members, and x2 is a direct cause of x1 in other members. So we know they're adjacent, we don't know the direction. Okay? So this pattern represents these two models. Now what do you recognize about those models? This is the example I just covered, right? And in fact, the true model I gave you was this one, right? And one of the models that we flipped to one edge was this one. And it turns out that this is the equivalence class, including the model we used to generate the data. Very easy to compute it, and it's very easy to see what's in it and what's not. Okay, now, instead of doing this hands-on demo right now, let me go back to that in a second and just tell you, I'm going to characterize equivalence for you because it's really simple and easy, and I think you'll like it. So, when are two models equivalent? If they have the two acyclic graphs, the two causal graphs for those two models, have the same set of variables, obviously, and they're de-separation equivalent, which is to say they imply the same set of constraints, independence-wise, if they have the same adjacencies and the same unshielded colliders. So an adjacency is when there's an edge one way or the other, we don't care which way, right? An unshielded collider is a little bit more complicated. In this case, y is a collider in between x and z because its arrows collide at y. Okay? That's what it is to be a collider. So here are four models that have the same adjacencies, but only this one has a collider at y. This is a non-collider, non-collider, non-collider. So all these three models have the same adjacencies and the same colliders. There are no colliders. And this has the same adjacencies, but it has a collider. A collider is shielded if the two guys that have arrows into the collider are adjacent in themselves, and it's unshielded if they're not adjacent. Okay? So the equivalence theorem is trivial. If I give you two models, you check to see if they have the same adjacencies. If they don't, they're not equivalent. If they do, and they have the same unshielded colliders, they're equivalent. They are the same de-separation equivalence. So if I look at these two models, right, you can see they have the same adjacencies and they have the same unshielded colliders because flipping the x2, x4 edge does not change x2 from being a non-collider to a collider. And there's no other edge I could flip that would preserve that. Because if I flip this guy, it changes x3 from being a collider to a non-collider. If I flip this guy, which is what we did in my experiment, I make x1 and x3, right? I make x3 a non-collider where it was a collider before. So if you can start with a model, you can say, add any adjacency or take away any adjacency, boom, it's not equivalent. But stay with the same adjacencies and flip an edge and ask yourself if you've added or subtracted any unshielded colliders. If so, then they're not equivalent. And if you've not changed the unshielded colliders, they're equivalent. Simple as that. Equivalence among latent variable models is more complicated, but it motivates why, in some sense, this part of the theory is reasonably simple and tractable. once you're dealing with patterns. Okay, so now, hands-on, I want you to go back to that session, right, in which we had all the different variants of that thing, right, that I built, and I want you to actually perform a search, and I'll show you how. So I'm going to go back to what I told you to label as session 2. Oh, I didn't do that. Okay, so estimation 2. It's this thing where I have this graph, and from this graph, I parameterize it, instantiate it to generate data, and then I have estimators from other models. But to do a search, you click on the search node, put it onto the workbench, and drag data into it. And in this case, all we need is data. You can also add background knowledge. I'll get to that in a minute. And then double-click on the search node, and you're asked, well, what kind of search do you want to do? Because there's lots. So you can do any of these searches if your target is what's called a pattern, which I just explained. And if you want to include, right, the assumption that there might be latent common causes, then PAG search is one thing you can do. But we're going to just stay in the pattern search realm, and there's different kinds of pattern searches. And if you want to do a search that involves constraint-based search, PC stable, the PC pattern, these are all constraint-based searches. The GES is a scoring search, and it computes the BIC score for each model, each equivalence class, and then just does hill climbing to find the equivalence class with the highest or the lowest BIC score. Okay, so if I choose that, I get this. Now there's something I should show you that's very handy. If I go to the graph here, and I right-click, I get layout, and I can copy the layout here. And I can go in here and right-click and paste the layout, and it puts the variables, right, in the same arrangement spatially as the target, as the source. So you can see that in my search, right, I got the pattern of which this is a member of the equivalence class. Okay? Now, if you get a pattern and you want to see if that pattern contains models that fit the data, right, you can do another step, which is to say, okay, graph manipulation, choose one of the DAGs in the pattern, okay? And that's what you get. And what you notice about that is that some of the edges are in blue and some of them are in yellow. And what that means is the blue edges were oriented from the data, and the yellow edges are completely arbitrary. So do not depend on the information about the direction of the arrow from the yellow. There is no information in that. It's just picking one so that we can estimate the model. But the blue edges tell you something about the actual direction, right? The yellow do not. So it's trying to make sure, right, you know which is which when you go to actually report your results, right, or base conclusions on your results. Okay, so now that I have an actual graph, I can say, okay, put a parametric model in that graph, put an estimator. Oops. Right, and the estimator should have the same p-value as the true one because I found the true pattern. And any of the models I would estimate in this pattern have the same p-value. It might be good, it might be bad, but they all have the same one, so it doesn't matter. So that yellow edge is harmless if all you're choosing is the model fit, and you just got to make sure you're willing to be cautious about it when you make inferences. Okay? So go to your actual session where you have this worked out, do a search, get a pattern, choose a DAG in the pattern, parameterize it with a PM, estimate that PM, and then we'll go on. Okay? And what you can do, obviously, what I've built you up to now is you can build your own model, apply an algorithm, see what you get in the pattern, and see how the pattern corresponds to the true model. And in some cases, the pattern will have a lot of information about the true model. In some cases, it'll have very little. It'll always have the right adjacencies. But the orientation information, right, can sometimes be rich, sometimes be very uninformative. Okay, now I want to take a slight digression to explain to you how to add background knowledge into search, because that's important if you're going to analyze any data sets on your own. And then we'll go into the latent variable models, and things get really exciting there. And I hope that'll probably be all I get to cover. Okay, so just to remind you, right, when you do one of these searches, you're looking with the discovery algorithm for an equivalence class, and then the background knowledge you enter should eliminate, right, any models that don't cohere with or are consistent with your background knowledge. So I'm going to create this model, right, which has 5 variables, and I'm going to assume that these have essentially tiers in time. So that x1 and x3, right, are measured, let's say, in 2000, x2 and x4 are measured in 2005, and x5 is measured now, right? So the causal relations here, right, are consistent with that. There's no reason something in 2000 can't cause something else in 2000, right? The only thing that would violate the time order would be something in 2005 causing something in 2000, right, which we're not going to allow. And then I'm going to actually, in both no background knowledge and then using that time order background knowledge, show you the results of the search. Okay. So I'm going to say, give me a new session. Now, what I can do to make my life simple is go up to this template menu and then say, oh, I want to do a search from simulated data, and then it just pops all those nodes on their workbench right away in the right order with the right connections. Save a lot of time. Mandy's very happy, yes. So now I go into the graph and I'll build that graph, right? I better actually go back and look at what it was. 1, 3, 2, 4. Oops. Okay, I think it was like this. Okay, so that's my causal model. Say OK. Let's parameterize it as sim. Instantiate it. Fine. Let's make this big data, 5,000 data samples. Do a search, right? And if I do the PC algorithm, right, that's what I get. Now that turns out to be a perfectly accurate output. This is the only thing that I can tell from this data from this generating process, because there are no colliders in this model. And colliders allow you to orient. If you have a non-collider, you can't orient. So you can see, right, that I've gotten the adjacencies correct with this output, but I have no information about the orientation or the direction of the causation, and that is all there can be from this output, given the data is linear and the independence decisions are all correct. Now,
Where do you cut out the time order?
that's what I'm going to show you now.
That's
So,
another way of saying correlation does not imply causation.
well, no, because, right, I mean, even though I don't get causal order, I get an awful lot of information, like it says that x1 has no direct influence on x2. I mean, yes and no. Okay, now let me add background knowledge. And the way you do that is you say knowledge. Put that on the workbench, and then to tell the knowledge box what variables I'm supposed to have knowledge over, drag data into that, and then to tell the knowledge, right, that it's going to make a difference on the search, the knowledge has to go into the search. All right, so let's do the knowledge. Now the first option for knowledge is called tiers and edges, so like that. And then what it allows you to do is to orient or specify that the variables are tiered in terms of their temporal occurrence. And what that does is constrain the search to not look for anything in which a later tier is allowed to cause an earlier tier. It prevents that from being even searched for.
So you're determining the direction of the arrows already.
No? Some of them.
Some, yeah, but it's, right.
And I'm going to ask you exactly which. Okay, so now in this model, right, if I'm going to stay true to the tiers that I mentioned early, I drag x1 and x3 into tier 1, x2 and x4 into tier 2, and x5 into tier 3. So this box says you can forbid the possibility of causation happening within a tier, or you can allow it. Let's allow it. So the only constraints that this imposes on the search is that x2 can't cause 1 or 3, x4 can't cause 1 or 3, x5 can't cause anybody. Everything else is allowed. x1 could cause x3, could cause x2, could cause x4, could cause x5, or it could cause nobody. Everything else is allowed. Okay, save that. And now if I do the search, that's what I get. So if I do the same search with no background knowledge, that's what I get. Now, explain to me which of these edges were oriented because of background knowledge, directly, and which indirectly.
X3 to X2 is directly.
x3 to x2 is directly,
X4, X5.
x4 to x5 is directly, and
X2 to X4 is
x2 to x4 is indirectly. Excellent. Right? There's no background knowledge that makes this edge get oriented. It turns out that once these guys are oriented, right, if x4 was going into x2, what would be produced? A collider at, oh, you guys are really good. A collider at x2. And that would be taking you out of the equivalence class, in which case I have no colliders, and so I can orient this, right, because of a combination of background knowledge and what the data says, right? And so this is very typical of background knowledge. Sometimes you put just a little background knowledge in here, and it indirectly ramifies into orienting almost everything. It's extremely cool, right? So background knowledge is really, really important. Yeah.
It seems like we're running the risk of over-specifying because we think that things could have influenced the previous years because they were measured later. They could have been present earlier despite being measured later. Like
Yeah, that's a great point. So you have to be really careful, right? So if you have a time series, right, like TV watching and obesity, right, and you measure TV watching in 2000 and obesity in 2005, right, and you make the assumption that obesity can't cause TV watching, well, since they each persist over time, it might be the obesity is causing TV, right, and they're each persisting, and it looks like they're associated even though the causation is backwards. So you got to be very careful about that and what that actually ramifies into in background knowledge.
You say colliders are important to get the directions going.
Mm-hmm.
Could you apply this to like an application, like for instance, if somebody takes a lot of drugs together into reactions and stuff, could you apply the collider thing to something pragmatic?
Sure, but I'm going to have to learn more about the case and be specific. But I mean, the collider idea is if the causal structure is such that we have a collision, right, then what happens in terms of the dependence or independence we should see in the data is different than if there's a non-collider. So it's really a mechanism to help you predict whether you will see a certain kind of prediction in the data or not. Now, I can go, and if I have time, I will get to it, but I want to get to the latent variable search, and then anybody who wants, I will show in the slides. There's an awful lot of interesting stuff to talk about with colliders, why they act the way they do, etc. Sergey?
So what if you have 3 parents instead of 2? Can you swap? Is it a collider? Can you, like, if you swap 1, you still have 2 other parents?
I'm not getting it.
What? Instead of 2 parents, 1 child.
Yeah.
In a collider. You have 3 or more.
Yeah.
Do you still change the relationship? Do they still change equivalence class if you flip just 1?
Yes. Yeah. So colliders are now, you have a threesome of variables, and it's got to be unshielded.
Yeah.
So the endpoints have to be non-adjacent. So any change in the unshielded colliders changes.
So collider will be 2 and more parents.
Yeah. Yeah.
All these we talk about, does it depend on the study design? I'm asking about like dependent sampling kind of data.
I'm assuming I have IID samples.
Everything has to be.
No, but yes, for the basic perspective I'm offering, yes, IID samples. Now there's very, and we'll hear more about it this afternoon and tomorrow. There's very interesting schemes in time series models, right, which we know not to be IID, but which we move into some approximation of IID with creating stationarity or creating, a windowing effect so that we're assuming we get to something approximating IID.
In the knowledge panel study, can we, a variable appear in multiple tiers?
No.
Why?
Well, because then it couldn't cause itself. I mean, no, because it can only occur in one tier. Now, what you can do though in the knowledge is instead of looking at the tiers, you can go to edges. And this is a representation of what are prohibited or what are required. So if I want to say, look, I want to add a required edge, I don't care what you do, right? x1 must be a cause of x2. It represents that in green. And if I say I want to add a forbidden edge, right, where I say, okay, x3 can't cause x4, I can do it like that. So I can very specifically require certain edges or prohibit certain edges. A tier will simultaneously prohibit several edges, any of which go backward in time. So it just means you have time when you're prohibiting causation backwards in time. Yeah?
In this setup, what's the difference between a prohibited edge and no edge?
A prohibited edge means in no equivalence class can that edge occur. No member of the equivalence class you output can that edge occur. No edge says I'm agnostic, it could or it couldn't, I don't know. So it's just a question of how broadly you're going to search. Okay. Okay, I did all this. You guys got that right? Okay, now I want to go to PAGs, which are latent variable models, and allow you to search for equivalence classes that include latent confounders that you might not have measured. So here's a bunch of interesting cases, and I'm going to cover one of them, but I urge you to take any of these models, build it as a graph, generate data, search, see what the search outputs, and see if you can predict what it will output. And it's interesting. So this case and this case I'm not going to cover. This case I'm going to cover because it's going to be an illustration of how this kind of search technique differs from regression, right? And you'll recognize it also applies to that Timberlake and Williams case that I did originally. Okay. So in a partial ancestral graph, right, which I represent one possibility of here, the equivalence class of models it represents include models with latent variables that I've left out. So in this case, x1 and x3 are adjacent, x2 and x3 are adjacent, right? But the arrowhead on this side and the arrowhead on this side indicates that whatever the connection is between x1 and 3 and x2 and x3, there's a collision at x3. But this circle means I don't know what's going on this side of the edge. It could be out of, in which case x2 is a cause of x3 directly, or it could be into, in which case there's a double-headed arrow, which means there's a common cause that's not been included among my models. So the simplest possible member of the equivalence class is just the no latent variable model. x1 is a cause of x3, and so is x2, and that has a collision at x3. This model, right, has the collision at x3, but now it's got a latent variable that's a common cause of x1 and x3, so the edge that, right, goes to x1 is into x1 through that arrow. So there's that circle in the PAG, and there's one of the ways it could be, right, covering, and there's the other. That's out of, and that's into. And so all these models are the equivalence class and an infinity of others. Because as I've represented things here, there's only one latent variable between each pair. There could be 2, 3, 4, 5, and infinity. Right? Compactly, when I say there's a latent variable here, I'm indicating that there's at least one, and there could be any number of them. Okay? I've also left out a possibility that I didn't draw, which I should, which says that there's a common cause I've left out, and there's a cause. Why not have both? As long as the arrow, right, is into x3 at this part of the connection, then I'm consistent with the equivalence class. And as long as I'm not adding any adjacencies, I'm consistent with the equivalence class. And what it tells you essentially is the ancestral relationships, especially the negative ones. So this says x1 is not a direct influence on x2 or vice versa, nor is there a latent common cause of x1 and x2. There's no adjacency of any sort. And it says that x3 is not an ancestor of x1. It has no causal influence on x1 whatsoever, nor does it have any influence on x2. It might be the case that x1 influences x3. We can't tell. And just from this kind of information, which is independent information, nobody else could either. There is no information you could get in the data that tells you that. You'd have to actually have more assumptions, different parametric family, etc. Now, there is an interesting case, right, where you can get causation from correlation, right? And here's one of the cases, but there's many, many more. So if it turns out that X is a direct cause of Y, and there's two other variables that are not adjacent, but are both connected to X and into X, they're both what we call detectable instrumental variables. They form instruments that we can detect their instruments, and then they actually orient the XY edge, right, as not only direct, but unconfounded. So just from a certain pattern of correlations, which essentially say that Z1 and Z2 are independent, Z1 and Y are independent given X, Z2 and Y are independent given X, I can infer this PAG, and in this PAG, the representation of the equivalence class only includes models in which X is a direct cause of Y and they're not confounded by a latent common cause. So there are cases, right, in which you can actually do a fully oriented causal direction just from observational data, but you have to be lucky. You have to observe an instrument. Yeah?
Just a question, in the bottom left, for example, could there be from Z1 to XP a direct connection and a common cause?
Yes. Yes. But there is no, in no member of this equivalence class is there a common cause between X and Y. And in no
T1 and T2 were identical.
Z-
Down the
Z-
bottom right-hand corner. T1 and T2 are this. If T1, if you instead of T2 on the right-hand side, you had T1 and T1.
Yeah.
Then that would be a common cause for Z1 and Z2, would it not?
Yes.
Okay. So then it's a
That is prohibited by this representation.
Okay, good.
Right, because they're independent.
There we go.
Yeah. Okay, and so here's what the edges mean. If they're not adjacent to the PAG, they're not adjacent to any model that generated them, right? This means that X2 is not an ancestor of X1. This means almost nothing. I mean, I hate to say it, it doesn't even mean they're causally adjacent, right? Which is unfortunate and is a little bit more complicated than I want to get into right now. This means everything you want it to mean. It's a direct cause, and it's a direct cause in every member of member of the equivalence class, unconfounded. And this means a lot also. It means that X1 and X2 have an unmeasured common cause that you left out, and I can tell you left it out. So you can detect that you've got confounded data in certain situations. Okay, now let me show you exactly the situation where all this occurs. And you can go back and generate this by yourself. Okay, so one of these things I think had it. No. Okay, so now I'm going to build a model with latent variables. So in this model, right, I'm going to make this be Z1, so it corresponds to the PowerPoint. That be Z2. That be X. That be Y. Now, if this in fact were the model that was generating the data, and our question was, is X a cause of Y? Right? That was our main question. And our approach was, let's measure X and Y, and let's measure any other variables that we think might be confounders of X and Y, common causes, right, that would explain or produce covariance between X and Y that wasn't causal. And the standard strategy that we teach, right, in most social science courses or psychology courses is, if your observational data looks like it has an association, throw in covariates and try to eliminate the association by controlling for them, and if you can't, then you might have a cause. Okay? So here's a case where you can do a real lot better. X is definitely not a cause of Y, right? It doesn't go through Z, nor does it go through Z2. Right? I'm not going to get any I won't get measures on L1 and L2. I'm parameterizing this as a sim. If I do a search and I use the FCI algorithm, I'll get a PAG. And there's the PAG I got, and I was lucky. And that's quite informative. What that tells me is X is not an ancestor of Z1, it's not an ancestor of Z2, therefore it can't be an ancestor of Y. It tells me there's a latent common cause between X and Z2 that I've left out. It tells me there's a latent common cause between Z2 and Y that I've left out. I don't know that Z1 is a cause of X, but it might be. I don't know that Z1 is a cause of Y, but it might be. But I've learned an awful lot about the structure that's producing this data. And let's compare what I get when I do a regression. Now I want to emphasize that in this kind of a situation, right, both Z1 and Z2 might occur prior in time to X. There's nothing inconsistent about that. So part of the advice you get when you're doing social science is look for covariates that might be prior to X, and they're associated with X, and they're associated with Y. And that is satisfied by these variables in both cases. Drum roll. P-value on the X coefficient is at 0.0000. So X and Y are highly associated once I control for Z1 and Z2. Now what I can tell you is, right, and I can tell you from the model, and if you do separation, you could tell me too, right, that if I don't control for Z2, right, then X will be screened off by just Z1, right? And if I go back and look at the graph, Z1 is a common cause of X and Y, and so if I control for it, right, I eliminate the association it produces, and there is no association via this other route, but I induce association by controlling for Z. So I must control for Z1, I must not control for Z2, and in a regression context, there's no way to tell that. So if I stick in Z2, leave out Z1, I'll get the same problem. They both look like they're significant. The only way I can discover this is to only control for Z1. But if you do a causal search like we did here, right, you can tell right away, if you know a little bit about deseparation in this graph, that if you want to get a consistent estimate of the effect of X on Y, or the association of X and Y that's, right, causal, you must control for Z1 but not Z2. And that's a little bit longer a story, but I won't go into it. Okay? Now, if you remember the Timberlake and Williams case, right, it looked just like this in the output. But we'll go back to that in a minute. Okay, so here is a set of instructions for how to do this hands-on. Why don't you go ahead and do that? So generate, right, the data from this graph, right, and then when you get the data, do a regression and do a search, and if you want to do a PC search also, and you'll see that the PC search tells you that the class of models you're searching for at the PC is the wrong class because it has a double-headed arrow, which cannot be possible if the PC algorithm is correct. And then we'll finish, right, I'll give you an overview. I want to finish by having you go back to the charity data set and enter the background knowledge that's appropriate for the tangibility condition being exogenous, and then search for a model and see if you can find one that fits this data. Right? And we can call up the researchers and say, we found you a model. Okay? Since we're out of time, let me just show you very briefly what's on the rest of the slides so that you can understand, if you are curious in your off hours on a Saturday night, what you might do. And of course, we're eager to have you come to the rest of the workshop. Actually, let me just get a show of hands because we're going to use this room at 2 o'clock. How many of you are having to go away, or how many of you are going to be able to come back at 2 o'clock? Okay, we're going to need more chairs then. Okay. Now, this is just a brief overview of the search methods. There's lots of constraint-based searches. There's lots of scoring-based searches. There's also latent variable model searches that are different than the ones I've shown you, that are specific to what we call psychometric models, in which there's a latent variable that has several things that indicate it. And there's been, in recent times, these wonderful promulgation of algorithms that actually deal linear but non-Gaussian variables, and you can learn more about the causal structure than I've described to you today. And there's lots more. There's models of cycles, there's time series models, and you'll see examples of all that later on. And Frederick Eberhardt will hopefully give you an overview later today of the state of the art. So I've given you the very beginning, and he'll give you the very end, and then it's up to you to go to the middle, which took me 10 years. So, and Isabelle Guion will tell us a little bit about this wonderful community that she's built around machine learning and causal inference, people to participate in causal challenges where there's a data set provided. We try to figure out what the causal structure underlying it is and compete in lots of different ways, and she'll describe that community too. There's additional slides. I go through the constraint-based search and sequentially show how it's done and what we actually test for on an example. You get a chance to do that. And then I give you the bridge principles that are the philosophical underpinning of all this work to say, what is it we're actually assuming to connect causal structure in red with probability in green? And it's quite simple. And then deseparation, how that works. And I have this other assumption, which I didn't discuss, faithfulness, which is very interesting. And then I'll do the colliders again. And then I do the explanation intuitively of why colliders produce association. And then do deseparation fully. So I was a little ambitious, didn't quite get to all this. Difference between experimental and statistical control, which is fascinating as a topic. And then regression as a causal inference. And that's it. So I hope to see all of you later, and thank you so much for coming. And please feel free to email us if you have questions, and if you have data sets that you're confused about how to actually use this on. We always learn a ton about people, about this project by having other people actually try to use it and come up with stumbling blocks and other things. So that's to our benefit, and we're more than happy to at least try to help you or ask Joe to change the program so that you have what you need. And Lizzie has an announcement.
Also,